Shaun O'Meara, CTO at Mirantis. We'll talk about the IaaS stack and we'll talk about a demo, and Angelica will support me on that again in a moment. All right, so what are the key requirements from an IaaS stack at the end of the day? Some of these are fairly obvious, but I want to call them out because we don't always think of it this way. They have to be manageable. It seems obvious, but there are many systems that are put in that are managed through CLIs or hands-on keyboards things. That's not manageable. That's not repeatable management. That means somebody in a data center plugging in a serial cable into the back of the switch. That's not manageable. Mm-hmm. They have to be improvable. We have to, and this comes back to what we were talking about with YAML, we have to be able to constantly be able to improve the state through configuration or through extension of the system. Observability is really deliberately on the bottom left corner there, because if we cannot observe our environments, we do not know what's going on, and we cannot do anything else that's on this. Right. They have to be controllable. Now, I know manageable and controllable seem like maybe the same thing, but controllable here is talking about being able to force a state, not just change a state. Mm-hmm. And that's where I talk about reconciliation, where I talk about being able to understand if something has changed. And then I need to be able to manage performance. It's AI. The performance stack is so critical. The way that we connect the app to the infrastructure has changed. We no longer abstract infrastructure. And this is a key thing that we have to be able to take into account. So that's making my point. AI apps are performance bound beyond just GPUs. We have this thing, we come along, oh, it must connect to the GPU. No, we have to connect to the GPU. We have to connect to the RDMA network. We have to connect to the storage networks. We have to understand how the storage is distributed within that network. How do the GPUs attach to block storage or object storage? How do I get data in and out of the clusters fast? East-west and north-south traffic has to be dealt with. Yeah. If I want to start sharing this infrastructure, how do I manage into the VM and into the Kubernetes components, whether it's VM or Kubernetes, to ensure that the PCIe is correctly allocated within those nodes? Mm-hmm. This is starting to become really, really critical, because if I take a GPU that's in one PCIe network and put a network card that's in another PCIe NUMA node, I'm going to have performance issues. Right. So I have to solve for that. And that's what we're doing with the IaaS stack. We also have to solve for multi-tenancy. Multi-tenancy isn't a simple thing. It has got many different aspects within an environment. It's not just a single, I'm going to take a node and make it. What if I'm doing multi-tenancy in virtual machines and I want to split a node or split those 8 GPUs between 8 different customers? How do I ensure, even down to the network layer, that I still have multi-tenancy? And how do I give options of cost value for multi-tenancy? Strict multi-tenancy, where you have the network and a node to yourself, comes at a different value to multi-tenancy done as a cluster on top of a shared infrastructure. So we have to think of multi-tenancy at different layers of the stack and how it connects all the way through.
Go back to that for a second.
Sure.
So what's missing from this is you don't show anything about the memory for both the CPU and the GPU, which might be entirely different memory banks.
Absolutely. And I'll get there in a little bit when we talk about the NUMA nodes and things in a moment. But I had to create a balance of making this chart actually seeable versus what level of detail. But you're absolutely right. The memory is a critical part of it, because the memory is dependent on what GPU, what NUMA node, what CPU it's put within.
Okay.
And how do we clean that after?
If you're managing things at the NUMA node level, do you also have the capability to attach CXL to this?
In theory, yes.
Okay, thanks.
I say in theory because we haven't tried it yet, but we have the capability to configure it. So, again, we're just talking about multi-tenancy. I won't spend a lot of time on this, but realistically, these are the 3 models we typically see in the real world today. We see full isolated or silo type multi-tenancy, where it's either a single node, a single scaling unit, or a single whole superpod type model given to a single customer, managed as one entity. Obviously, full isolation, strict isolation, it's the strongest isolation you can get, but it's also the most expensive way to do it. And as we start to change the workloads and get to smaller workloads, this doesn't make as much sense. And it has an enormous management overhead. The hybrid or cell-based model, this is the VM model. This is the AWS, this is the Azure, everybody who's sharing VMs across nodes. Now, this is where it gets more complicated because I could have a VM. I could take a couple of nodes and put them together. How do I create smaller units of service that I can offer customers? And this is probably, these two are the most common models we're seeing in GPUs at cloud providers today. The shared model, though, is becoming a lot more prevalent. I'm buying just an inference service, which just needs a slice of a GPU, meg, or one GPU or two GPUs. How do I share that? Excuse me. How do I share that in a Kubernetes cluster so that the user is abstracted from all that complexity? That's the more shared model. Not strict isolation. There's always risk in that. But for most workloads, most startups or people just experimenting with LLMs, it doesn't matter. So this is where those three models that we're seeing today.
Do you help support service lifecycle and promotion, not to mention, pipeline and that sort of thing, to help maintain service consistency, support rollbacks, like all of that sort of thing?
That's all part
because
of it.
Because what you just showed, I look at it and I'm like, well, what I'm probably doing with probably 20 services, 20 AI related services at the moment, not to mention more, is I'm starting on the right and I'm moving towards the left.
Yeah. So this is where the whole
previous slide is what I'm
this is where the whole templating and template chaining model comes into the process, because we have these immutable fixed templates that handle the deployment and the lifecycle of the components. To move them forward or back in time, it's just a change in that immutable template object. So I can roll back and I can roll forward simply by
programmed change. So to
programmed change.
Okay.
It's a lot easier to do config management when you have a small number of elements to config. When you have tens of thousands of elements that are very similar, you want to start making those config elements immutable. And there's some very interesting things being done. There's some new companies starting up that are actually starting to look more into that as a bigger picture at the moment. We're working closely with them. I'm not going to spend a lot of time on this, but I want to just show how that stacks up at a architecture level. And the reason I put this up mostly is just to call out the fact that this management layer sits outside of the stack. It's the meta control plane that sits outside the stack. It is not in the data plane for the stack. And it allows us then to manage the various layers of complexity as you build up the stack. And we'll go into a more technical diagram in a second. The key thing is we're able to operate both at the infrastructure layer, the compute layer, which is essentially the operating system, and the host management layer. And then we start to layer on the different platform components on top of that. And by defining all of that in one place, you can start to do that, the Lego building blocks type model, but all in one set of controls. So let's talk about the IaaS stack. So we start at the top of the stack. If you think about it, bottom up, top down, however you want to think of it, the service management layer. These are the things that your end users actually interact with. It's the tools that run on top of the environment. It's the kube flows, it's the ML flows, it's the web services, whatever might be running. Those are all defined as the service layer. We have our centralized control plane, which I've spoken about. We have bare metal and network automation, virtualization platform, and then obviously Kubernetes as a service is key to our whole offering. So if we stack up how this would look, and obviously this is a architecture, very simplified diagram of the full complexity. If you look on our website, there's a version of this that goes right down into the DPU networking layer and how we manage the DPUs and do network isolation at the DPU layer. But essentially, stacking it up, we have bare metal management that does the bare metal host management. And if you imagine there was a layer of DPUs underneath here, that would also be managing the DPUs. We have the storage management layer, not depicted. We have the network management layer, also not depicted for simplicity. Then we have the K8 fleet layer. And this is where we start to layer in those services and capabilities. So for example, we have a Kubernetes cluster. We put KubeVirt on top of that. That KubeVirt allows us to deploy VMs in a very complex, aligned to the PCI and the NUMA nodes. And then we can start to put Kubernetes on top of that. And you can stack up your service layers. We even have the ability to connect these VMs, and if we have DPUs in the stack, to a specific interface aligned to only that DPU. Again, we're coming back to the whole host tenant isolation capability. And because we have a central point of control over the network, the host, the DPU in between, we can now align all of those tenancy and isolation capabilities right the way through the stack.
So, question on that, Jack Pollard with Paradigm Technica. So how do you enforce isolation and prevent breakout from a node to another tenant's environment?
So that depends on the layer of requirement, but primarily virtual machines, strongly configured virtual machines. And if you need deeper isolation than that, then a whole node to a tenant.
I'm sorry, I didn't hear the last part.
A whole node to a tenant.
Okay, so you can isolate and
we can isolate
to a tenant.
It's configurable. You basically have to. So this is where the templates come in. We create a pattern in the templates, and then you just request that pattern depending on what your needs are.
Okay.
So we take all that configuration complexity away and put them into templates.
And so the only enforcement, though, is just by placement of the workload.
It's workload placement.
In there.
Well, I mean, on the nodes, for example, we're configuring the C groups so that there's no crossover between the VMs. There's a lot of host configuration components. We're also making sure, for example, that there's no shared NUMA nodes across the VMs. So we can configure, and that's in fact is the next slide. As we start to look about how we configure the virtualization space, we're able to match the physical node configuration into the virtual machine. And then at the network layer, we're creating that same level of isolation. So if I have the DPUs in place as an example, the DPUs present a VIF into the host. There's no host access into the DPU configuration. That VIF can only be linked to a specific virtual machine. Even if that virtual machine dies, I cannot connect another VM to that same VIF without reconnecting it, reconfiguring it. Mm-hmm. There's no way to do that. Now, can you break out of a VM? There are ways. Mm-hmm. We're protected against most of them in this day and age via configuration, by KVM's capabilities. Are we looking for that in our monitoring? Certainly. Everything comes with an inherent, some layer of risk. But what we're also saying is, if you want true multi-tenancy, you can't put Kubernetes at the host layer and try and do vClusters or something like that, because those are inherently unsafe. Mm-hmm. Yes. Kubernetes by nature, even well-configured Kubernetes, is relatively easy to break out of into the host.
Right.
So that's why we now layer up these layers of, and it creates a certain level of complexity that we're trying to handle, but that's how we layer this up. Hopefully that answers the question. Okay. Let's talk about virtualization for a second. So virtualization up till now, and I mentioned this earlier, has been covered by this idea of abstraction of the infrastructure. So I create a VM, it generally can move around that infrastructure fairly easily. Of course, that changes when I'm running large language models that are bound to a GPU, bound to a network interface, bound to a memory bank, or any ML workload. It doesn't have to just be large language models. And that very much changes the paradigm. The old idea that I just start a VM and it doesn't matter more or less, maybe do some NUMA CPU pinning, has gone. We have to explicitly inject a configuration that matches the physical node's configuration. And so we've built a set of tools that sidecar the KubeVirt capabilities, that we're able to examine that in physical node's topography, the LS topper of that, and then match the VM requirement to that physical. And what you're actually looking at here is a LS topo depiction of a virtual machine's, the inside of a virtual machine. And you can see, if you know, it's a bit difficult to see here, but essentially we've got the 4 NUMA nodes. Inside these nodes, we've got 24 CPU cores, the NUMA node, the PCIe, and the GPU that is plugged into the InfiniBand card, making sure that it's on the same PCIe slot as the GPU, so we can align that performance requirement. We're working closely with NVIDIA on this to prove this virtualization stack. We have a requirement to be less than 5% performance overhead across the entire solution. We believe we're even better than that right now.
How closely tied to NVIDIA
infrastructure? We're primarily on NVIDIA infrastructure today.
Yep.
But we are supported for the other major players as well, and we have certifications with AMD.
Okay.
But 99% of the customers we have today are NVIDIA.
That's market share.
Yeah. But we can, as time goes, we can definitely extend further than that.
Is that true at every layer? So with an AMD solution, it's also whatever networking is behind that.
Correct.
That's obviously not going to be.
We're going to come back to that whole provider plugin model. I can start to add those providers, and we can start to even extend those capabilities and even have heterogeneous environments where we have multiple different vendors in the same environment, because you're creating a contract.
Right.
That contract is related to a set of templates. And I keep coming back to the templates, but once you kind of understand how we're trying to handle the templates, this is where the whole power of the solution really comes in at the end of the day. But this idea of contracts is incredibly important as well, and we'll touch back on that. So,
hello again. All right, let's see this in action. So we'll start with demoing how our platform streamlines the onboarding and the provisioning process. This feature enables a platform operator to onboard bare metal in just minutes. So let's go ahead and start this video. This dashboard provides real-time visibility into server status and resource usage, guiding users through the workflow required to initialize, configure, and prime bare metal for production-ready AI, Kubernetes, and virtualized workflows. Users can filter and sort through their server inventory, ensuring their right resources are always organized, accessible, and ready for use. Whether that be by mostly recently created servers, IP, tags, or specific keywords. So with our platform, users can follow the lifecycle of their bare metal servers. So starting from discovered, available, provisioned, and use. During the discovery stage, it inventories the hardware and onboards servers to be managed by Cordant. So once we're onboarded and available, we can remotely access our servers and carry out actions such as reboot servers, upgrade firmware, and other advanced configurations. So we're going to start by provisioning a host. So we're going to provision our operating system here. Users can choose their operating systems, such as Ubuntu, Red Hat, or Windows. Users can also provide their own image URL here. So below is the form to put important information such as network name, SSH keys, and user data. Advanced configs can also be done with the built-in YAML editor as well, as shown here. So once you're satisfied with your choices, all you have to do is just hit the provision host button and you're done. Provisioning infrastructure can be streamlined and tailored to your use cases. So let's take a look at our bare metal instance details. See, we have the status degraded, and then we have our statuses provisioned, and here is our details. We offer base level observability, essentials such as CPU usage, memory usage, and disk usage for resource monitoring. Alerts can also be enabled so operators can stay on top of their resource usage. And here on screen, we have the audit log, where you can watch a timeline of your server's lifecycle, view what actions are taken and by whom. And then we're going to move along to deploying a Kubernetes cluster on bare metal. Clusters can be created via the platform. And as you can see, we have several cluster templates to provision our cluster. We can choose between a basic editor with simple drop-down menus and presets available, or we can use the YAML editor for those who want to add advanced config. We can take the nodes that we've provisioned as well and assign them wherever we see fit. So here we have Kubernetes small, Kubernetes medium. And then let's go ahead and look into our observability. So after creating our cluster, we can monitor and observe the cluster's resource usage. We click here again. We can see all of our cluster information. We have the monitoring dashboard. And then we also have the cluster topologies. So let's get a better look at that. So at our top layer, we have our tenants. Below, we have our virtual machines enabled through KubeVirt. Each virtual machine is assigned to a node in each tenant. Alternatively, we can view all this information about the base cluster, VMs, and our child clusters through this table. Vital information such as networking components, pass-through of GPUs, memory, storage usage, and OS image are all stored here. Through the Coordinate platform, we can provision a bare metal server.
Can you actually show the network topology?
Not on here at the moment.
Through the Coordinate platform, we can provision a bare metal server, deploy a virtualization platform, and provision virtual machines on physical servers fast.
Is KubeVirt the only virtualization platform supported?
No, we support OpenStack ourselves, so we can do a large-scale OpenStack deployment as well. It actually sits on top of the previous generation at the moment. We're moving it on top of Coordinate.
Okay.
So we have a previous generation product, which is what Coordinate was built off, which is MCC. And we can deploy OpenStack. If you have VMware,
yeah,
we can support VMware.
Okay. But
So we can
pretty
deploy
much where the
onto
line
VMware.
stops. Yeah.
Well, we can. There are other virtualization platforms we can support, but we don't deploy and manage those ourselves. That's obviously, if you've got a large-scale VMware platform, we can deploy onto it. If you've got OpenStack, we can deploy onto it. There are other vendors in the pipeline at the moment. Do you want to talk about those, or should we?
We have a custom request for mechanics. One, and then I think there's another one that's mixed in there. But
Okay.
yeah, I mean, that's the mode that we're in right now. Like, it's a very customer-centric thing. As we sort of find like a unique requirement from a customer, we build that out.
Gotcha.